Hello, we are now entering section 7.3, which deals with confidence interval for a proportion. Now, if you recall, a proportion is just a part of a whole. So for example, if 3 people prefer learning online out of a group of 10 people, then your proportion would be 3 out of 10 or 0.3. Let's take a look at an example of how we can apply this to solve confidence intervals involving proportions. So an example would be the following. Assume that a student wishes to estimate the proportion of students who transfer from a community college to a UC. The student selects a random sample of 40 students and determines that 8 of the students are transferring to a UC. Also, the student wishes to be 95% confident in the estimation. Okay, so that would be an example, and we'll work this example out in a bit, but we're going to talk a little bit about the theory behind estimating these confidence intervals. So first of all, P is the population proportion. This is the value that needs to be estimated. So P will be the value that we're estimating. That's our population proportion. We will use, and this symbol here is called P hat as the point estimate for P. So P hat will be computed from the sample and will be used to estimate P. So P hat is a single value that is only used to estimate P. Turns out every time we collect a sample, we'll get a different P hat. Thus, instead of relying upon one P hat, we'll just create a range of them to estimate P. And so this range can be represented as P hat plus or minus some margin of error. And this P hat remember, will not deviate too far from P. Thus, we're going to have a range in which we add and subtract this margin of error from our P hat to estimate P. We're also going to need Q hat. So Q hat is a proportion representing those students not transferring to a UC. So Q hat is always computed as 1 minus P hat. Something else we need to mention: in order for P hat to be normal, we need N times P hat and N times Q hat to both be greater than or equal to 5, where N is your sample size. So it turns out that the margin of error is Z times the standard deviation, which in proportions is represented by radical P hat times Q hat over N. Thus, we have a formula for our confidence interval. We're estimating P at the center, and we're just taking P hat and subtracting the margin of error, which is represented as Z sub alpha over 2 times radical P hat Q hat over N, and we're also adding that margin of error on the right side. So this is the formula that we shall be using to determine the confidence interval of our proportion. So let's work out the example that we mentioned above, which is this example here. So the first step is we're going to calculate P hat. So we have 40 students, 8 of them are transferring to UC, thus P hat is 8 out of 40, which is 0.2. Q hat, the proportion of those not transferring to UC, is 1 minus P hat, 1 minus 0.2, which is 0.8. And then Z sub alpha over 2, remember, we can turn the table F, look up our confidence level, which is 95%, and determine that the Z value is 1.96. So we now collect this information and we plug it into our formula. So P hat becomes 0.2, Q hat becomes 0.8, Z sub alpha over 2 is 1.96, N is 40. And we just use our order of operations to calculate, and we end up with P, the proportion of those students transferring to UC, falling between 0.076 and 0.324. And if you want, you could convert them to percentages. We can just say, thus the estimated proportion of students transferring to UC is between 7.6 and 32.4%. And then I have a few examples for you to try. We're going to work one other example out. All right, we're going to look at this example here. So it says the total number of people who prefer watching basketball versus other sports is 22 out of 60 randomly selected sports fans. We're going to once again use a confidence level of 95% to determine the confidence interval of the true proportion of sports fans who prefer watching basketball. So step one, we're going to compute the sample proportion. So p hat is x out of n. So remember, the smaller number is always on top, bottom number at the bottom. 22 out of 60, we always round to 3 places, 0.367. Q hat is 1 minus p hat, so 1 minus 0.367, 0.633. We take this information along with 95%, that's going to give us a z-value of 1.96 from table F. We're going to insert that information. The only numerical value that will not be inserted is a value for p. And it's we perform our computations and we can see that, and be careful how you read this final result. Think of the less than, the two less than's as the p is between this point and on the left and this point on the right. So p is between, somewhere between 0.245 and 0.5489. And so that's how we compute confidence intervals for proportions. Now the last part of 7.3 has us compute what are the sample size for proportions. So we say a common question in statistics is how large should a sample be? Well, constraints in determining the sample size are time and money. Thus it is wise to make some effort to determine the sample size prior to computing a confidence interval for the proportion. And this is real important for you to remember, is that anytime a sample proportion is unknown, the standard value to use is 0.5. And so the margin of error is typically provided in this computation. So we have our formula for the minimum sample size. It's n is equal to p hat times q hat times z sub alpha over 2 divided by the error squared. E is the allowed margin of error, and we always round n up to the next whole number. Okay, so let's go ahead and work out this example here. It says, assume that a school nurse would like to estimate the percentage of students who have not been vaccinated at a local Cal State. She uses a nationwide statistic as her sample proportion. It is 1.4%. Also, she wishes the margin of error to be within 5% and the confidence level to be 95%. So we're going to convert the decimal, and we're going to convert the percent to a decimal. We just drop the percent sign and move the decimal 2 spaces to the left. Okay, so we know that p hat will be 0.014. 1 minus p hat is 0.986. 5% converts to 0.05, and if we look up z in our table F, that's going to be 1.96. Insert these values into our formula. Perform the calculations. We end up with 21.2, and we round up to 22. And that's how we compute the minimum sample for proportions. And I have a few problems for you to try. And there it is. We'll go ahead and stop right here. We're done with 7.3.